regress, sort of unmeasurable errors, right? It could come from the device used to measure things. It could come from the fact that you truncate numbers after a certain number of decimals. There's sort of this immeasurable error. So even if you knew the right function and you had all of the data, you would still maybe have some unmeasurable error. So there's multiple sources of where error can come from. So in simple linear regression, we start out with a very simple function that relates y and x, which is essentially the equation of a line. That's why it's called simple. That's one variable, linear regression. So, and we covered this in stat at some level. The intercept, the slope, right? And this is a hypothesized model. We don't know if it's true or not. So what we do is we estimate it. And this is where the notation gets a little messy. We estimate the slope and intercept based on the data. So B0 and B1 are the estimates of beta 0 and beta 1, right? And so essentially what we're saying is the relationship is linear. Of course we know it's not really. And we use this little hat to indicate that we're estimating. So in a picture, what does it look like? Very small picture. You've got some data points, they have x's and y's, and your estimated equation is some line, right, that in some sense is best. Here's where the first part of the class ties, or the part of the class we just finished ties to this. In fitting this line, you're actually measuring distances from the point, vertical distances from the point to the line. These are called residuals, and you choose the line. You choose the line in a way that minimizes the sum of squared residuals or sum of squared errors. So B0 and B1 are the solution to a nonlinear min problem, basically. All right, you won't really need to know that, but just want to point out that that's actually happening. We may go more into that later. What we're going to do, by the way, is we're going to review this in Excel, and then we're going to give it a shot to do it in R afterwards. All right, so that's kind of going to be our flow. We'll go through a number of examples, and then we'll build up and get to the R part. So let's look at the first example, which is this Bergens of Norway. I'll give you a little bit more context. If you download the not completed version, you get this little data set. You might remember it after we look at it. This is for people who go camping. Anybody in here go camping? Is that a popular sport around here? Right? Sometimes city folk aren't very outdoors oriented, right? But I don't know. Some groups of people, maybe the Czech people are into going outdoors. I don't know. Every time I turn on Eurosport, it's skiing and shooting. There must be a big skiing and shooting championship going on now, whatever sport that is. Biathlon, right? It's probably a pretty difficult sport, right? But get a lot of adrenaline, then you have to stop and be very steady, right? So anyway, here we have price, which is what we're going to try to forecast. And its price is a function of the rating of the sleeping bag. And the rating of the sleeping bag, unfortunately, is in Fahrenheit, so it's going to be hard for you to understand. But Fahrenheit is a temperature scale like Celsius, where 32 is equal to your 0, right? And so if it's below 32, that means the sleeping bag is rated to a pretty cold temperature, right? And if it's above 32, like this one, then it's more like a summertime sleeping bag, right? So what would you hypothesize would be the relationship, or at least the general relationship between rating and price? As the sleeping bag is rated for colder weather, the price would be more expensive, right? And that's probably because the materials are going to be more expensive. So in Excel, first thing you can do is you can always look at the relationship between two variables. Excel doesn't do this very well, but I think if you highlight the data with the headings and say insert scatter diagram, we did this before, you can see that relationship is negative, right? As the rating, as the temperature goes up, the price goes down, so to speak, or as the temperature goes down, the price goes up, right? And I think I already told you this the first day, but one of the nicest things in Excel is you can get the regression line right on this, you can get the regression equation right on this picture, right? Or just remind you, just select the data, right mouse click and say add trend line, and you can look at the linear or other forms of the equation right on this. Right on this. So there we have it, right? We don't really need any more sophisticated tool. So once again, just to remind you of some useful and relevant diagnostic statistics. Obviously the correlation is one thing, we haven't computed that yet. The R-squared is another. In simple linear regression, these are very closely related actually. The correlation is just the square root of the R-squared, but that's not true in general. So the R-squared here is 0.8043, so 80% of the variation in price, right, that's our Y, is explained by the rating. And in real life, that's a pretty strong fit. I mean, that would be good for one variable. You're explaining 80% of the variation. Now, built into that rating is like the quality of the materials, all that kind of stuff. So I think, for somebody doing, some kind of forecasting, R-squared is a very good fit measure for, at least in linear regression. Okay, we talked before also about the slopes, the estimated slopes, so you can see it there. And we're going to run the regression in a second to remind you how to do that. Then we'll move quickly on to a more difficult example. But you can see that the slope is equal to minus 0.527. So you would say something like for each degree, I would say it in a negative way. For each degree cooler, for each degree, let's see, so sometimes you have to work on these interpretations, but for each degree colder, that the sleeping bag is rated, the cost increases by $5.27. And I'm pretty sure I generally emphasize this pretty heavily in the first class, so we already learned that, right? So if X goes down by minus 1, right? Y goes up by 520. Actually, 528, I guess. Right? And, that makes sense, right? Again, the cooler the bag, the colder weather that the bag can keep you warm, the better quality bag it is, so you would expect to pay more. V0 is equal to 359 and some change, 27. Sometimes we don't care about the intercept, very often we don't, we just leave it in there anyway. Here it has a nice interpretation, right? For a bag rated 0 degrees F, it would cost an estimated $360. Drop it a little bit. Okay, for a bag rated 0 degrees F, right? So 0 degrees F is pretty cold. It's like minus 20 C. So that's like camping outside in the mountains in the winter or something. Has anybody ever gone winter camping here? I've not ever done that either. I have a brother who climbs mountains in the winter and skis down them and stuff, so it's kind of crazy. crazy guy.
So can you read again for each degree colder?
Yeah, so for each degree warmer, it would go down in price by 527. So I said for each degree colder, it goes up in price.
It's just that I can read.
Oh, you
because
can't read it, yeah. That makes perfect
It's
sense.
not because your handwriting is bad, but it's there are like space spots,
Yeah.
so it's hard to.
Yeah, so for each degree colder, but the sleeping bag is rated, right? 1 unit change in X to the negative, right? For each degree, again, poorly worded. It could be, as the sleeping bag's rating decreases by 1 degree, the cost increases by $5.28. That help? Slightly? Not getting a lot of positive vibes from that there, Katerina. Let's run the regression in Excel. Do you guys remember how to do this? Under data, there is an option called data analysis. So quick and dirty statistics is all here. Unfortunately, it's limited in terms of what it can do, but it can do regression. So if you scroll down, there is regression here. And when it says regression, it means linear regression, and it can do simple linear and multiple regression, which we'll do in a minute. So you put in the Y variable. Notice I'm putting it in with the heading. You put in the X variable. Notice I'm putting it in with the heading. You select the labels because you put in the heading. And voila, you have run your first regression. So I do most of my stat teaching in Excel because it's, intro stat, because it's very simple to do this. Okay, were you able to find the data analysis add-in and run the regression? I usually do a little bit of post-processing. One thing I do is get rid of decimal places because Excel gives a lot of them, and then I also highlight the whole spreadsheet and widen the columns a little bit so we can see it a little better. Okay? So here's your model down here. Right? There's your intercept and your slope. All right, any questions? Pretty easy, right? All right, so in traditional statistics, this class will sort of evolve out of, but in traditional statistics, what you do is, first of all, the R squared is high, so you know the variable is probably a good one, right? You only have one variable, but the other place the other thing you were supposed to take away from statistics is about the p-values. So do you remember the saying, when P is low, ho must go? I hope you remember this saying, because how could it ever leave you in your brain, right? When P is low, ho must go, okay? It's a joke, all right? Maybe you know the English slang about ho, but maybe not. Yeah. So, but let me take you really quickly through the hypothesis test that's there. Okay, and again, this is sort of just warm up right now. Not the kind of thing, this isn't the kind of thing that you would probably remember, right? So, the null hypothesis is that the slope is equal to 0. The alternative hypothesis is the slope is different from 0. We would test this hypothesis with a t-statistic. We don't need to do it this way, right? We would get our estimated slope and we would subtract 0 and we would see how far apart they are. Well, if you remember from statistics, we see how far apart they are by dividing it by some measure of error. All these numbers are actually here. The estimate of the slope, of course, is minus 5.28. We already talked about that. So we're really asking how many standard deviations are 5.28 and 0 apart, right? There's a formula for computing the standard error of the slope, and it's right down there, 0.87. The number is right down there, 0.87. So if I put that in, right, you can see that 5.28 and 0 are going to be more than 5 standard deviations apart. In fact, they're 6 standard deviations apart, 6.08. So minus. So if two things are 6 standard deviations apart, are they far apart or are they close together? They're far apart, right? So what this says is, based on this 5.28 estimate of the slope, that is far away from 0. Since that is far away from 0, the true slope is not likely to be 0. We're going to pick the alternative most likely.
Can you repeat that sentence?
Yeah, since our estimate of the slope, 5.28, is pretty far from 0, very far, right? And far generally, by the way, is like 2 to 3 standard deviations. I mean, even 2 is pretty far, but 3 is definitely far. Once you get up to 6 standard deviations, you're quite far away. Did you guys do any Six Sigma in operations? Right? So yeah, so the reason you set it at 6 sigma is because if you're going outside of that, you're really not in control, right? So that's the reason you set your 3 sigma up and 3 sigma down, right? So if Jacob and I are 6 standard deviations apart on some measure, we're far, far apart, right? And so
I'm sorry, so this T-stat is, but what's far apart? What two things?
From the mean, right?
yeah, so implicitly every coefficient in your printout, every coefficient that you estimate, here we estimate B0 and B1, are being tested against 0, Jacob. So we're asking if they're far from 0. Now there's no reason why you'd want to check the intercept to be far from 0, but the slope, right? If the slope, think about this. Here's my dots, right? Here's my x, here's my y. If the slope could be 0, what does that say about x explaining y?
There's no relationship.
There's no relationship, right? So you really do want to reject this. You want to say, no, I'm pretty sure the slope is not 0. Knowing x does tell me something about y. Okay? So we always test the slopes against 0, right? Because if the slope is 0, then knowing x is telling you very little about y.
Telling you how many standard deviations the slope is away from 0?
Yeah. So that's one way that's the way we operationalize the test, right? Right? In other words, if our estimate is far from the thing we're testing it against, right? Then we say, we're pretty sure it's not this, it's something different from that. That's how we sort of back-ass word logic, but that's how science works, actually.
So it's just saying it's very, very, very likely that they're related.
Okay, well, 2 steps. It's very unlikely that the slope is equal to 0.
Yeah.
So therefore, it's very likely that the slope is something different from 0.
Yeah.
So therefore, yeah, they're related. Okay? We might have already suspected that with an R squared that was that high, but, okay? So what you do in hypothesis testing, just to take this through to its sort of bloody ending, is you put it on a T-curve. In this case, the degrees of freedom would be something like 9, okay? Let's not worry about that really. And then you say, okay, here we are at minus 6.08. You know, really far, it's much further out there than it shows on the picture. And you compute the area outside of that, and that is the p-value. Actually, to be more precise, this would be the p-value divided by 2, because we would look at the area outside of 6.08 and minus 6.08 and add those 2 areas together, since it's symmetric. Right? So you can see what happens, right? The further away you are from the middle, the smaller the area in the tail, right? The bigger this number in magnitude, negative or positive, the further out you are, the smaller the p-value. So the p-value is here, it's 0 to 2 digits. If I make it a little bigger, you'll see it's not completely 0, but it's pretty dang small. So,
Wow.
okay, so it's not 0 exactly, but it's quite small.
I always thought that the p-value was like the accuracy, like if it's 0.05, then that means you're 95% sure.
Yeah, you're warm. So that's where we're getting to. So when p is 0.00, how many more zeros? 1 0 and a 2, let's say. Okay, right? We compare p to alpha. Right? P is less than alpha 0.05. So we reject
Oh, yeah.
H naught at alpha 0.05. P is also smaller than alpha 0.01. P is also smaller than 0.001, right? So we would reject it at all these other alphas. So what we really do in real life is we don't have an alpha. We just look at the p-value. And we say when p is low, almost go, right? Exactly.
So,
We don't say that out loud, by the way. We only say it out loud in this room. We don't say that out loud in public.
so we
Because
discussed you
your
for-
families would start to think this MBA program is really wearing you down.
So how would you interpret the 17.91 related to the?
Yeah, so again, we don't generally worry about slope being, the intercept being equal to 0, okay? Because just the intercept is just sort of a, I hate to say this, but sometimes I think of it as a nuisance parameter. It might have meaning in some contexts, like fixed and variable cost, if you're estimating that with a regression equation, could have it's fixed cost, right? But in many cases, it just doesn't have any meaning. And here we wouldn't expect this to be equal to 0 just from looking at the picture. So it's saying it's 18 standard deviations away from 0, but I would ask, why are you testing it equal to 0? Why would you expect a sleeping bag rated 0 to cost 0, right? So it really, in this case, that test has no meaning.
And can I ask, what's the real life interpretation of p-value? Like
Yeah, so that's a good question. So the probability, it's like one way to think of it is it's the probability that you went out and collected data, and if the true slope were 0, this is the probability that you got 5.28 for your slope estimate.
Doesn't
Okay.
make sense.
Yeah.
I don't understand what that means.
Yeah,
So-
me neither.
If there's no relationship between X and Y, how likely was it to see data that gave you a slope of 5.28?
Can you say it in a simpler way?
Very, very unlikely. Okay, almost infinitesimal, right? So therefore, your hypothesis about it being 0 is wrong. That's
So
one way to look at it.
if P is low, it means the two variables have a relationship.
Correct. Correct. That's the real operational takeaway. But the interpretation of the p-value is the probability that we saw the data we did, given the null hypothesis is true. Okay, so the null hypothesis would be the slope is 0. So well, how likely is it that we get 5.28 for our slope? Minus 5.28.
So can I say, so if it was 0.01, yeah, if p is 0.01, that would mean there's a 1% probability that you randomly got a result that agrees with my hypothesis.
Yeah, it's a 1% chance, right?
There's a 1% chance that the null hypothesis is right.
Yeah.
Why randomly?
It's telling you how likely or not unlikely it is that the result you got is agreeing with the null hypothesis.
That's right.
Okay.
So it's very unlikely the null hypothesis is true, right? So therefore, we reject the null hypothesis. All right, so I think